This is section 4.8, Newton's method. So why are we doing Newton's method? Sometimes we are presented with a problem which cannot be solved by simple algebraic means. For instance, if we needed to find the roots of the polynomial x cubed minus x plus 1 equals 0, we would quickly discover that previous algebraic methods such as factoring wouldn't work. However, we will see that calculus gives us a way of finding approximate solutions. Let's suppose that we want to approximate the solution to f of x equals 0, and that we have somehow found an initial approximation to this solution, x sub m. This initial approximation is probably not all that good, and so we'd like to find a better approximation. To do so, we will need to start by finding the equation of the tangent line to f of x through x sub n. Using the points x, y, and x sub n, f of x sub n, we would have the following equation. Isolating y in this equation, we get y equals f of x sub n plus the derivative of x sub n times the bottom, which is the equation of the red line on the graph. We can see that this line will cross the x-axis much closer to the actual solution to the equation than x sub n. Let's call this point x sub n plus 1, and we'll use this point as our new approximation to the solution. Since this point, x sub n plus 1, 0, is a point on the tangent line, we can plug this point into our previous equation and get 0. This equation can be rewritten as x sub n plus 1 equals x sub n minus f divided by the derivative of f. So we can find the new approximation provided the derivative isn't 0 at the original approximation, because if we get a 0, then we have a 0 on the bottom for the derivative, and we know that that can't work. This process can be repeated over and over to get a sequence of numbers that are getting very close to the actual solution. This process is called Newton's method. Newton's method uses an iterative process to arrive at the approximate root to the function. If the number x sub n becomes closer and closer to the actual root, r, as n becomes large, we say the sequence converges to r, and we write the limit of x sub n equals r as n approaches infinity. Example 1. Starting with x sub 1 equals 2, find the third approximation, x sub 3, to the root of the equation x cubed minus 2x minus 5 equals 0. In order to use Newton's method, we must first find the derivative. So we have f of x, and we have the derivative of f of x. Now we apply the method. So we're going to apply it into the following formula. We're going to have x sub n minus f of x divided by the derivative of f of x. Then, since we know x sub 1 equals 2, when n equals 1, we're going to plug this information in. So when x sub 1, we know that x sub 1 is 2, so we plug that in. And then we can plug in 2 to where x sub n is for all of those seen in this fraction right here. So we have 2 cubed minus 2 times 2 minus 5 divided by 3 times 2 squared minus 2, and we get 2.1. Now, if I want to find when n equals 2, we know n equals 1, so I can find the next set by setting n equals 2 to 2.1. And I plug it in and I get 2.0946. So therefore, the third approximation, x3, is about 2.0946, and it is accurate to 4 decimal places. So we can continue to do this until we get to what we knew. We knew x sub 1 equaled 2, but we did not know what x sub 2 equaled. When we find what x sub 2 equals, that's going to give us what we would plug in for x sub 3, so that is x sub 3. Use Newton's method to find the 6th root of 2, correct to 8 decimal places. So now we know that the 6th root of 2 is equivalent to x to the 6 minus 2 equals 0. Now find the derivative in order to use Newton's method. So first we need f of x, and then we need the derivative of f of x. and then we plug it into the formula. And now we can do what we did in the previous problem, and we get the following approximations on the next slide. If we choose x sub 1 equals 1 as the initial approximation, then we would obtain the following approximations from x sub 2 to x sub 6. Since x sub 5 and x sub 6 agree to 8 decimals, then we can say the 6th root of 2 is 1.1224625 to 8 decimal places. So first, find the derivative. Second, apply Newton's method. Third, plug in the appropriate numbers for x sub n until you get the desired result. And that's it.